Hi, let us talk about the analysis of reinforced concrete beam. You know that in the reinforced concrete structure, the beams are used to support the slab, whereas the slabs is used to withstand the loads, which are the permanent actions and the variable actions. The permanent actions and the variable actions normally appears in kilonewton per meter square. You can get those from Eurocode 1. This means that the actions acting onto the slab is quantified on the basis of the loading per unit area. The loads later shall be distributed from the slab to the beam. Depending on different aspect ratios of the slab, the loads carried by the adjacent beams differ slightly. In fact, Eurocode does not provide any guideline for you to analyze the load. For you to analyze the loads acting onto the beam, there are several methods. Among those popular include the U-line method and the methods given by British Standard. Both methods are applicable, but the calculated loads vary slightly. In these videos, we're going to compare the two methods used to determine the actions acting onto the beam. It is given that the design load equals to 10 kilonewton per meter square, and you are asked to analyze three types of beams. The aspect ratio of the slab, it will be 1:1, 1:1.5, and 1:2. First, let us talk about the U-line method. The U-line method demonstrates the possible failure of a slab when subjected to excessive load. When the slab is loaded to failure, large crack shall occur, and the orientations of the crack follow certain patterns, and this serves as the basis of the U-line method. To make it simple, for a slab subjected to the load, we will need to draw several lines in order to subdivide the slab into various parts for us to identify the loads to be taken by the surrounding beams. And those lines constructed onto the slab is known as the U-line. The figure here demonstrates to us how the U-lines are constructed for the slabs of various ratio. For any slab given, starting from a corner, draw a 45-degree line, and then you will do the same for the other corners, here and here. The inclined line shall meet each others at different locations, depending on the aspect ratio of the slab. If the aspect ratio is 1:1 here, this shall be the U-line. When the aspect ratio is 1:1.5, there will be regions of triangles and trapezoid. Same goes to the aspect ratio 1:2. This shall be the areas of the loads to be taken by the nearest beam. That means the loads of this area shall be taken by the beam here. The loads of this area shall be taken by the beam here. The loads of this area shall be taken by the beam here, and so on so forth. Once you have subdivided the slab, the next step is for you to quantify the percentage of that subdivisions. For 1:1 aspect ratio, this is quite straightforward. It is divided into 4 equal parts. Each constitute 1/4 of the total area of the slab. As for the aspect ratio 1 to 1.5 and 1 to 2. These are the percentage of the areas. Now, based on the areas distributed here, we can assume that the loads acting onto the beam will end up to be something like this. This represents the loads acting onto the beam with the triangle area, and this represents the loads acting onto the beam due to the trapezoid areas. However, for simplicity, we will assume that the loads is equally distributed throughout the span. That means we will assume the total loads of the triangle being divided by the total span, giving us a uniform distributed load. Same principles apply to this trapezoid load. Total loads divided by the total span, you get the uniformly distributed load. Now we will need to calculate the loads carried by the beam of the shorter span and the longer span. How do we calculate that? First, you will need to get the total loads divided by the effective length in order for you to get the uniform load. Now, how do you determine the total load? Since the loadings is given in the mode of kilonewton per meter square, that means your total loads, it will be your design load times the total area times the percentage of that particular part. Let's say you need to determine the loads acting onto the beam here. We consider this beam as the shorter span, in line with the definitions of longer span and shorter span by British Standard at 110, so that we can make direct comparison later. Your design loads is 10 kilonewton per meter square times the total area, which is 1 meters times 1 meters, and times the percentage, which is 25% to be carried by this beam. You will do the same for the rest of the beams. Taking this beam as an example, your design loads times the total area, which is 1 meters times 1.5 meters, multiply 33.3%, and then divided by the total length. That gives you 3.33 kilonewton per meter. As for this slab, you want to calculate the UDL acting on the beam here. Your design load 10 kilonewton per meter square, multiply the total area, which is 1 meter times 2 meters, and multiply the percentage, 37.5%. That gives you the total load. For you to get the UDL, you divide it with the span, 2 meters. Based on the calculations, you are able to determine the loads carried by each beams. As you can see, by comparing different aspect ratio from 1 to 1 to 1 to 2, the beam here, the UDL increases from 2.5 to 3.75. However, for the beams here, the UDL reduces. This shows how the loads are being distributed in the slab under different aspect ratios. Next, we'll deal with the British Standard method. Using same set of aspect ratio, refers to table 3.15 of British Standard at 110. We are talking about the Ly per Lx of 1.0, 1.5, and 2.0. The table 3.15 is used to determine the shear coefficients. These shear coefficients can be used to determine the UDL acting onto the beam. The shear coefficients beta Vx is referring to the shorter span, which is this span, assuming the shear force diagram looks something like this. Imagine that the same shear force diagram should go throughout the span here. It will end up to be an UDL acting onto the beam. That's why when you find the coefficients beta Vx, adopt it in the equations given by British Standard, it will end up to be the UDL acting onto the longer span of the beam. As for beta Vy, these beams are referred. In table 3.15, the British Standard classify the slabs into various categories, taking into account the numbers of the continuous and discontinuous edges, as well as their locations. This is an unique feature of table 3.15 as compared to the U-line method. The U-line method disregards the category of the slab. No matter the edge is continuous or discontinuous, the same set of U-lines shall be constructed. It makes no difference in terms of the distributions of the load. Whereas the British Standard, taking into account the redistributions of the stress as a result of the continuous edge. The continuous edge and the discontinuous edge will have different levels of rigidity that can affect slightly the amount of loads taken by the edges. So when we want to calculate the UDL acting onto the beam, since the questions do not specify what type of slab it is, and the purpose of doing these examples is to compare the analysis outcome of the U-line method and the one given in the British Standard. Therefore, we will need to find the suitable range of the loads if we are using the British Standard to calculate it. Therefore, when we deal with the 1:1 aspect ratio, it means that the Ly per Lx is equals to 1.0. Out of so many types of these slabs, we get the shear coefficients, the largest value and the smallest value under the columns of 1.0 Ly Lx. From the column here, we found that the smallest number is 0.24 and the largest number is 0.45. Now you may use these ratios for you to determine the minimum UDL and the maximum UDL. Use the formulas given in the British Standard. The coefficients times the design loads times the shorter span. The equation here is calculated on basis of the shorter span. This gives you a range of the loading between 2.4 kN per meter to 4.5 kN per meter. As for the longer span, we are referring to this column. The smallest number is 0.24 and the largest number is 0.45. Adopt the coefficients into the equation here. You get the range of the loading between 2.4 kN per meter to 4.5 kN per meter. Next, you do the same for the columns of 1.5. The smallest numbers is 0.34 and the largest numbers is 0.57, giving you the range of 3.4 kN per meter to 5.7 kN per meter. Then you repeat the process for the Ly per Lx equals to 2.0, giving you a range of 0.38 to 0.63. That gives you the UDL of 3.8 kN per meter and 6.3 kN per meter. For the shorter span, we are referring to the same column, and therefore the loadings remains. As you can see here, the UDL increases as the Li per Ls increases. This response is similar to the U-line method. However, as for the longer span, it remains the same, but the U-line method reduces. Now let us compare the result as obtained from the U-line method as well as the British Standard method. The result is summarized here. First, the U-line methods give you one exact value, whereas the British Standard method, it gives you a range of the loading depending on the type of the slabs. The estimations is close. Let's say for 1:1 ratio, the U-line method estimated 2.5 kN per meter, whereas the British Standards give a range of 2.4 to 4.5 kN per meter. As for the 1.5 aspect ratio, the U-line method estimated 3.33 kN per meter, and the British Standards give you 3.4 to 5.7, depending on the classifications of the slabs. What you see here, the British Standards is generally more conservative as compared to the U-line method, especially when it comes to the aspect ratios more than 1.0. The estimated loads, even the minimum loads, is always greater than what is estimated using the U-line method. Although the 1:1 aspect ratio is slightly smaller, but the difference is within 0.1 kN per meter, which is relatively small. From here you will see the conservative measures adopted by the British Standard. And because of this, the British Standards is more popularly being used in the analysis of the loads, considering the distributions of the slabs. It is easy to use, and you may use the British Standard to find the shear force and then the bending moment. You can straight away acquire the design moment and the design shear by adopting the equations given in the British Standard. And you feel safe using British Standard as it gives you some degree of conservativeness. In the case that you do not have the table with you where you need to do the design, the U-line method may be used, but you will expect that the loading it will be slightly smaller than what you can anticipate from the British Standard. Therefore, you can conclude that the British Standards analysis is more conservative. Bear in mind that for the analysis of the load, as recommended by the British Standard, is that whatever shear loads that you have acquired, such as in the range of 2.4 to 4.5, the uniform distributed loads, it shall be applicable to the middle 3/4 of the overall span. The British Standard assume concentrations of the loads at the center part of the beam. However, normally we will adopt the simplified method. Assuming the same magnitude of the UDL is applied, and it is applied throughout the entire beam span. Knowing now the UDL estimated in the British standards is slightly more conservative than the U-line method. Now if we adopt the simplified method, the conservativeness increases, where this area is not considered to have any loading by British standard. Instead, we are considering it into the simplified method. Now it depends on you. You may choose to follow strictly to the concept of the British standard, or if you are doing the manual calculations, assuming the same uniform distributed load, throughout the entire span, it will be easier for you to analyze the shear and moment. Only that you will anticipate slightly bigger moment and shear loads.